So we have now time for open discussion. If there will be not enough discussion, we can continue contribution from people who sent some emails who couldn't come. But I hope we can discuss. I think it's an important issue. And this particular discussion was generated by Simon, because he asked about the role of the decoherence. I kind of make a crusade. The decoherence doesn't make any role. One disagreement was resolved. It's just semantic, because I always say the coherence with environment doesn't make any role. And when I discussed with David, he said that internal degrees of freedom of a system, it's environment. And for me, internal degrees of system is a system. So then this is important. What I mean, there is no meaning, it's not important, because if I have a macroscopic system in two macroscopically different states, I think they cannot interfere, never mind if somebody will put large effort and make some isolation and prevent entanglement with environment, which is external system. So maybe Simon will say that it's the same, or what you had in mind, or what people, that there is a kind of general statement, Oxford School, that many words was kind of science fiction until Oxford said decoherence, and now it's a good theory. May Simon will be the first to make kind of, to see if I present it correctly or I mislead it full concept.
Here. Doesn't work.
Hello? Oh, that's better. Right. So in general, in decoherence theory, it's not very different from what one's trying to do in non-equilibrium statistical mechanics. One's trying to extract relatively simple equations for some subset of the degrees of freedom involved, and you have perhaps reasons to believe there is an interesting subset of the degrees of freedom such that that is possible. So one way of putting it is in terms of fast versus slow degrees of freedom. You try to integrate out the very rapidly changing stuff in order to arrive at the slowly changing stuff, whereby you take into account that rapidly fast changing stuff. You try to take it into an account. Or if you're integrating out the environment, you try to take into account the influence of the environment on what you're looking at, the degrees of freedom that you're interested in, and you're looking for simple equations. And we find them. We find them quite a lot, and there's a lot of hard work that's gone into it. And this is really making up most of the collection of models that we call decoherence theory. But in terms of why is this important to the Everett interpretation, I think that in a way the insights that we gain, for example, are related to why are the stable states that make up Everettian branches, why do they have a classical character? And the answer to that, you can look at this in terms of master equations for, some molecule in a heat bath or something. How is it interacting with its surroundings? If it's interacting through local interactions, then the relevant states that are picked out by this business of integrating out and finding simple equations will be ones that are well localized in space. If you had an interaction with an environment that was mediated by momentum, for example, there could be different answers. So you do get out, and you can look at exotic sorts of decoherence and get out very interesting kinds of typical kinds of states that satisfy relatively simple equations for isolated degrees of freedom after integrating out all of the others. And this is a whole body of phenomenology. So here's a way of doing Everett. Start off with heavy particles in thermal environments, deduce, and this goes through ideas of Zurek, Jauss, and Zeh, or if you really want a completely soluble model, the Caldera-Leggett model, which is oscillator degrees of freedom. And of course, a heat bath with radiation is normally oscillators anyway, but it's the issue of the heavy molecule. What is that? Is that an oscillator or not? So what you learn from this is that these fairly heavy particles will be well localized and unable to interfere with one another. So superpositions of such will be unable to interfere with one another. And one can then build up to more and more complicated systems and get out a branching structure where there's no reference to experiments at all. This is just branching as goes on in nature all the time. So just on that last note, I think that one of the reasons why a lot of people rejected Everett was because it seemed that branching was only defined for Everett given an experiment. You had to have the experiment before you had any notion of what were the branches. The branches were defined by the outcomes of the experiment. And I think for a lot of people, this wasn't much better than Copenhagen. Copenhagen also with Bohr, it's only given the context of an experiment that you can say anything meaningful at all. And it seems likewise with Everett. It's only given a context of a measurement that you can say anything meaningful using Everett's ideas. And worse than that, it would seem that prior to, this is a point John Bell made, prior to quantum mechanics, prior to humans making quantum experiments, what sort of branching took place? And it's a question I have for you, Lev. So prior to 1900 or 1850 or whenever you think quantum experiments started to be performed, what sort of branches were there in the universe, in the multiverse? What defined them? How do they arise?
So really there is a difference between Oxford, it looks like many words, and my many words. If you will have branching, you have regions which really cannot interfere. But these regions are not macroscopic objects. I will not say that there are many words. My words, I need macroscopic object here or here. The fact that there are kind of microparticles and maybe if there is a whole room here in particular quantum state, and then neutrino changes them to orthogonal states. And now we have superposition of all this air in one state in orthogonal state, and they do not interfere anymore. I will not say that the word split, or didn't. Word split, I have a definition which is vague, but I need macroscopic object in macroscopically different state. So if you don't do quantum measurement, no splitting, no new words. Sometimes nature can have. There was supernova explosion, and as far as I understand, some of them really have real quantum origin, and so maybe you have a supernova explosion now, and 1 year later or 1 second later. So clearly, stars are macroscopic objects, and if they are in macroscopically different states, these are different branches. But if you have all kind of microparticles which do not make objects which we consider relevant for us, then in our world, there is no splitting. Splitting is only, we need quantum measurement. So until Geiger counter, single photon detectors, and all these things of broken fluorescent lamps, which work quantum mechanically, were very small splitting. I put my word splitter, I increase splitting by a lot. We need quantum. We need amplification. We need exactly one Neumann scheme. When we have quantum superposition of a microparticle, making macroscopic object in two different places. This is what makes splitting. Otherwise, it's not. I don't care in which states are things which are not relevant to me. There is all macroscopic objects are the product state in every world, and there is a rest. And the rest may be very, very big, very big. And this very big may be very entangled, and I don't care about it.
Okay, if I can just respond briefly. In my framework, my understanding of the Everett interpretation, there's no such thing as a quasi-classical domain that deals with everything. I mean, we're not there. So we set up a quasi-classical domain for something rather restrictive, a certain sort of regime, a certain kind of numbers of degrees of freedom, rather restricted in scope. And how you fit together more and more complicated systems, that's a very interesting question. And I think that applies to absolutely all attempts at making sense of quantum theory and building up to something like a macroscopic world. But insofar as you will give me a certain amount of, charity and I don't know what, optimism about how to do this, I will end up eventually with lots and lots of fine-grained branches, many of which differ from one another in tiny ways. And if I course grain over those small differences, I will then end up with branches in your sense, Lev. I will recover your macroscopically differing branches. So it's not that what you're talking about is crazy or, I don't know what, incompatible with what I'm talking about. I get what you're talking about. I arrive at the same picture that you do if I just choose to coarse grain and not look closely at the minutiae of these, tables and chairs and so forth and what's going on. So I can do that. In the other point you're making, you seem to grant that, well, it is slightly strange to me, the idea that before human beings started doing quantum measurements, there wasn't really any branching going on in the universe, and now there's been a whole lot of it. My goodness, what a huge impact we humans have had. We created a multiverse out of nothing. It almost is a reductio ad absurdum. I'm sorry to say, for me, Lev, it's almost a reductio ad absurdum, but never mind. Let's not use names. But you do seem to grant that... You do seem to grant that there may be some quantum events taking place in stars that could have macroscopic consequences and so forth. So I think I'll just push on that and push and push and push, and I'll say, yes, tell me more, tell me more, tell me more. Now, when you do that, and you're telling me more and telling me more, you will have to start to engage with the question of how do microscopic events amplify up to the macroscopic level in nature, not when we're doing experiments, in nature. And that's exactly the business of decoherence theory.
Claire wants to just give a little presentation, show that between you two there is a less disagreement than you think. Just.
Okay, so I prepared something. Perhaps I will say very much similar things that already said. Anyhow, decoherence is around anyhow, whether you like it or not, first of all. Then, secondly, in a measurement, we need decoherence because otherwise the pointer of the measurement will be in a macroscopically, the pointer is macroscopic and it will be in a coherent state, spread out, and we don't want that. So you need decoherence in a measurement situation. Then, because otherwise the pointer will be in a superposition, macroscopic superposition. And we need to explain why we don't see that. Because that's what the logic says. Otherwise, you have some alternate Trumpian logic, I think. And an argument already, now this was transferred from making this on the Mac and then over to PowerPoint and sort of things happen. But for cosmology, and that was already mentioned, I think, and there is a discussion. Sudarsky is sort of saying that decoherence doesn't work in cosmology. Sudarsky says that in cosmology, decoherence doesn't work, and so that shows that it's important. And I think for sure it works. And the picture there is of three macroscopic objects, and say they have already formed, and they are in a superposition state, so they're not just at this point, but everywhere combined, any combination. And then you put in a gas that interact with them, and then you will have decoherence, and it will be exactly as Simon said, that there will be macroscopic states, but it's very fine-tuned, just a little change, then you're almost in a new branch, and then you change a little bit more, and just come into a branch which is almost orthogonal, etc. So it's sort of rather subtle, but still works. And then I have one comment about macroscopic objects, and if we can have coherent phenomena with macroscopic objects, the answer is yes. There's nothing that prevents that in principle. You can have any large, if you just keep the temperature low enough and no disturbant environment. But there's two things. So, because you can have intrinsic decoherence, but you need not have that. So you can have a very big object, like the universe. And have, so, because in a sense, when you have actually spontaneous symmetry breaking, it's a sort of, from one base to the other, a coherent phenomena. So yes, you can have very big states in superpositions.
Crucial point that the measurement can happen without any decoherence. If I'll spend $1 million preventing decoherence with environment, the measurement will be okay. This is my pointer, this is 0, this is 1, and this is 2. And my quantum measurement apparatus, when I bring a quantum microstate in a superposition of 0, 1, and 2, will make, I don't have the third hand, it will be superposition of these three things. And of course, I'm not in a 0 temperature. If it's just moved by 1 degree of freedom, I will not say it's a different pointer. It's a real pointer. So clearly, when it's here, it's internally different, and there is no chance that today or 100 years from now, I will be able to make interference with this kind of pointers. If they entangled with environment or not entangled with environment, I don't need any environment to prevent my possibility to interfere. And this is what I think the decoherence mean.
I think you're fundamentally wrong. It doesn't matter what size of the object you have. If I turn it, if I don't invoke the internal degrees of freedom, if I don't make things wobble inside.
Yeah, I agree, but you cannot do this in real life.
Yeah, so you have, then you refer to that there is internal decoherence. And so that's just one form of the decoherences. So then you cannot deny that there is decoherence.
Yes, in 90% of places, people talk about environment decoherence. And this is only what my objection, not internal. Environment is not relevant. What's the only thing which is relevant? When we have macroscopic objects. And we have enough internal degrees of freedom. And I agree that if I have a cat and just move it translationally without changing its internal state, it's not 2 words. So I need a dead cat and a live cat. They are macroscopically different in many parameters. And I don't need air there. I can put them. I can keep him some kind of internally alive.
Thanks. I mean, just a couple of comments. I mean, one of them is just on this internal thing. Again, I don't think there's disagreement here, but perhaps it's helpful just to think as a model. I mean, to first approximation, an insulating solid object is a phonon gas. You know, it's internal degrees of freedom. You can think of as a gas of free phonons at lowish temperature. A phonon gas can decohere stuff just as happily as a photon gas can, and even the math is going to look pretty similar. The more substantive thing I wanted to say goes back to the Simon-Lev exchange. I mean, I think chaos is important here. So chaotic processes and other unstable processes like this, characteristically, at the classical level, give you exponential sensitivity to initial conditions. Translate that into a quantum situation, and classically chaotic systems go macroscopically indeterminate on a timescale that's linear in their Lyapunov timescale, their instability timescale, and logarithmic in their action. And as we all know, logarithmic in I over h bar. And as we know, logarithms go up super slowly. So even very big systems, I mean, one of the moons of Saturn is one of the nicest examples of this. Even very big systems go quantum mechanically indeterminate if you treat them as completely isolated center of mass degree of freedom only, on timescales that are actually, you know, of the order of hundreds of days and things like this. So I think that those kind of classic chaotic phenomena are the kind of go-to example you want of ways in which nature generates decoherence, and also ways in which, if you want to continue studying the dynamics of systems, you're going to need a bit of decoherence and a bit of care, because it's not, you know, if I've got regular dynamics and it's not chaotic, then just very straightforward undergraduate problem sheets will always tell you, look, here's my system. It's this much spread out, even without an environment, even by itself. It won't over the age of the universe. It won't spread out much more. But in a chaotic system, that's generically not going to be true because of the exponential dependence. And cosmology is a case study for this. I mean, we don't need to think about like hypothetical models of how decoherence in cosmology might happen. We have quantum mechanical models of structure formation in the early universe, and they have exactly this character. We have inflaton fluctuations. Those fluctuations, because it's gravitational, I've got gravitational fluctuations have an instability. They tend to grow rather than shrink. That's our mechanism for structure formation. We can, you can track that through. You can look at the fact that superpositions on that scale are going to have to decohere. You can decohere it with short distance fluctuations in the same fields. You can decohere them with other fields. I wouldn't want to claim that the sort of inflation early universe models are undeniable, but they're fairly robust, very well studied, in conformity with predictions, and just give us cosmological decoherence playing out very directly.
Elitzer?
Oh, the time for my question is past, but I may return to it. What about an avalanche, Lev? There are cases in which a single grain of snow on a mountain, whether it falls or not, will create a macroscopic object. So such amplifications you have every place, say in the desert where there is a rock up there and going to fall. So far I didn't know that you believe that most of the splittings of the universe come from planet Earth or in other places where there are sentient beings. That's not what you meant, of course. Or is it?
Okay, but may I just...
You're a dualist. All those years, you believe that... Okay.
No, let's be, to be a little more...
Patience you have... Okay, thank you.
Let's be a little more careful. When you go to my homepage and use word splitter, if I want to believe the people who said that they really connected to a quantum device, they claim that they do, then I'm certain we split the word. There are some papers which says that if I'll do this, and it's published, I think, in Physical Review, I split the word because there are quantum uncertainty in my fingers. And I'm not sure that they are wrong. I think they are wrong. Because, and I would like, because I want that the world continues and we can behave. If it's split all the time, it's very difficult to make kind of decision. It's not supposed to split seriously. So I think they're probably wrong. But even if they're not wrong, those number of words, it's bigger than I thought it. But it's not a big, I don't think it's a big problem. I completely agree about chaotic system. And I think I agree about your example with the avalanche. It's kind of, there is a good chance that it's really, there is a quantum superposition of killed people and not killed people in an avalanche. Most probably. This physics is extremely complicated. And in chaotic system, I think you can really calculate and say that this is what's really happening. Non-chaotic system and macroscopic objects standard uncertainty relation doesn't lead to spread it. You don't need environment. I think once I never was able to find, once I thought I read a preprint by Coleman trying to say that the environment extremely important for stabilization of bodies. And then it was in a time when there was no internet. And later I was trying to find it and never found it. I don't believe it. If somebody knows what I'm talking about, it will be interesting because he really claimed the difference. He said that the environment, this is what makes things stable and we need this decoherence with the external environment. Again, I'm not sure, and if it's true, it will not change much. But first, it's not necessary. This is kind of my main point in the whole story. The many words will work well if this external decoherence with environment, this mechanism is not efficient. It still will not change the story about many words. When we perform experiments, and I think it's most important for experimentalists. They fight decoherence to make, we're trying to make this experiment with single photons or other things. It's very important to keep everything coherent.
Just want to repeat that in general, those of us who think decoherence is teaching us something important, we can coarse grain and arrive at your picture of many worlds. And it's not that there's anything wrong with it. For most experiments, your picture works just fine. But the point about, and I think what's happened at the Oxford side, is there are many more questions than we have than you are curious about. And it seemed to us that it was important to answer those questions. For example, what are the origins of classicality? Those questions are important for us. For example, what happens in the natural world before, those questions are important. They're not important for you, Lev. You're happy to analyze experiments. And for that limited purpose, other than in chaotic situations and so on and so forth, you don't need decoherence, I grant you that. For the purposes that you put many worlds to, you don't need it much. Occasionally you will, chaos and so on and so forth. So I would wish that you would accept a sort of a bit of an olive branch here, that this is something where we can agree on.
Just 2 points. Classicality, to get classicality from decoherence, I don't think it's so simple, and I don't think it's needed, because we live in a branch and we have information about our branch. We don't know the wave function of the universe, so we don't need to know how to take wave function of the universe to get branching system, branching structure. We sit in the branch. What we need is our branch is not interfere with others. We need much less. So if the other thing is difficult, it's not a problem. And also I believe that when I have 2 detectors and a single photon, then I will say, and the detector identical, will get 2 words. And you somehow said that there are many decoherent words which will give you probability. I don't believe in this story. So I really, you probably want to get more, but I believe it's impossible. And when we try to get impossible thing and fail, this is, I think, get bad publicity to many words. This is, so I want to make only statements which I believe are true.
Yeah, okay, I'm just curious, I mean, I agree, certainly the decoherence happens. What I'm sort of wondering about, is that sufficient for giving precisely what the branches are, for giving a preferred basis? And if not, what else is needed? I mean, is there something about our consciousness that makes us always see things to be in macroscopic positions that would not be implied directly by decoherence, or does decoherence? Because a lot of times, if you take the density matrix of one of these decoherent things, it really is spread out a lot more. I mean, in these models where you have harmonic oscillators coupled to a heat path, if you took the density matrix of the object, it's still just as much spread out as before. So I'm just trying to think, is there a preferred basis you get from it, and if so, how?
Okay, so as I had in my poster, by the way, the decoherence literature is somewhat confusing, I think, because one talks about the preferred basis or the basis given by decoherence, and that's a mistake. It's a question of that we have macroscopic objects, and we are a macroscopic object, and we probe the world with our means, which essentially is where are things, and so that's the way. And what decoherence theory shows us is that the coherence length after decoherence is very small, so that the macroscopic objects interact with each other or see each other as localized, reasonably localized, but not perfectly, because we all expect that microscopic objects have some wave function which is narrow but with finite width.
David?
So this is mostly on the Simon-Lev exchange a moment ago. I think you were being offered an olive branch, Simon. I think you were being offered an olive branch. You were being offered the observation about internal degrees of freedom. And I think this is right, and I think it's a genuine communication weakness in the Jurek tradition of doing decoherence, which, while formally it applies perfectly well to internal degrees of freedom, absolutely tends to have as its go-to example the radiation field, the atmosphere, and I do think it confused me for some time to understand what's going on there. I think it is an awkwardness of the language of environment-induced decoherence that the Jurek tradition introduced, that it leads to exactly the communications issue we've been having. I think it's much clearer, actually, in the way that people in the kind of Halliwell tradition were speaking about decoherence, where the examples and the ideas were much more about internal degrees of freedom. I think the other thing that comes from that tradition, this is relevant to Don's point, and again it's recognised by the Zurich tradition but less explicitly visible, decoherence is a diachronic process. The task of decoherence is not to diagonalise the density operator. The task of decoherence is to suppress interference between branches as an ongoing process. That's explicit in the decoherent histories formalism. It takes a bit of work to tease it out of the density operator formalism. But what matters in the density operator formalism isn't that you statically get a diagonalized matrix, it's that what you get is an evolution dynamics on the density operators, which has the formal form of a probabilistic dynamics without interference, without cancellation. That's what's telling you you've got a branching structure. You can't always see it if you just look at the density operator in isolation.
Wait.
Yeah.
Okay, oh yeah.
I mean, let me say that when we just because the microphone makes it awkward. The only other thing I was going to say to Don is that I think this issue about what we can perceive is one place where I think the Zurich way of talking is pretty helpful. If you've got decoherence, and then if you imagine trying to build a physical system that's sensitive to degrees of freedom that are fighting the decoherence basis, that's going to be extremely difficult. And I think as you need, that's not going to be persuasive if one has a sufficiently radical anti-functionalist conception of mind, but on fairly weak assumptions about how the mental has to cohere with the physical, it's going to be very hard to have an information-producing system that can see and remember and record and act on facts that don't sort of conform to decoherence. At least that's how I think about it.
So maybe you'll answer, but this Dowker-Kint thing seems to say the decohering histories, you have all these different all these different sets of decohering histories. And is the ordinary decoherence also give a huge number of sets of things that decohere? Maybe.
So, Patsy, you want to answer?
Maybe Simon wants.
Thank you. Yeah, the Dowker and Kent business was entirely about consistency. It wasn't about decoherence in a more full-blooded sense, and nothing like their result applies to the concept of quasi-classical domains, for example. So, I mean, I think the right picture of consistent histories or quantum histories formalism is extremely weak, it's extremely flexible. You can cast almost every model of decoherence involving master equations and so forth into a decoherent histories framework if you wish. Whether it's calculationally superior or not is something we can disagree about. But Don, can I just come back to your issue here with what the mental, as it were, and with consciousness. And again, this connects back to Lev. So the question would also be this: decoherence theory is relevant to extracting a meaningful theory of molecular kinematics, molecular interactions, how they actually work. Typically, again, in thermal environments. And we build up actually to biochemical processes. Through decoherence theory, we can see, or hope to, anyway, give a decent analysis of how biochemistry emerges in the natural world, again. So these are sorts of questions that, Lev, you're not addressing, and in a way you're not interested in them, though I do recommend them to you. I think they are fascinating questions, but that's just got nothing to do with the measurement problem. That's been your stance, Lev, and I understand that. But again, for those of us who are interested in a broader spectrum of questions, decoherence is rather important.
But is decoherence not, if you don't restrict it to the decoherent history things, is decoherence, does that pin down the set of states more precisely than decohering histories? Decohering histories says they have the consistency thing, but then there's a huge number of sets of decohering histories.
Consistent, that would
Sorry?
Call them consistent sets or consistent histories rather than decohering histories. They're not really decohering. I mean, that's Bob Griffith's point. Consistency is a very formal condition, and it's a very weak condition. And Kent and Dowker only address that. But coming back to the biochemistry business, the point is, if you've got a brain made out of biochemistry, if that's how your brain is operating, then of course you'll be seeing things that are quasi-classical insofar as biochemistry is quasi-classical and it's embedded in a quasi-classical environment. You could see nothing other if you are built out of biochemistry.
Yeah, it seems reasonable. I just don't quite understand how the decoherent histories can have a huge number of different consistent sets, and yet decoherence somehow seems to narrow, or at least it sounds like the claim is it narrows it down, that there's only some of those decoherent histories are actually correspond to what we observe. I mean, how does it get narrowed down?
I don't think it does get narrowed down within a quasi-classical domain. I mean, you've got large numbers of histories within the quasi-classical domain. And the great, the amplitudes are peaked over those that satisfy quasi-classical equations. So, how do they differ from one another? Well, they differ in things that we would put down to quantum contingency. Where we say, oh, something happened.
Saying there's a whole lot of different bases, in other words. I mean.
No, it's always, the quasi-classical domain, it's always the same basis. It's a single basis.
Well, that's the part I don't, why is that more restrictive than consistent histories have a whole lot of different possible bases? In other words, there's one set that.
There are many, there's a continuum infinity of consistent history spaces. Indeed.
Right.
And that's just not true of quasi-classical domains. Quasi-classical domains are few and far between. It's hard to find them.
Okay, and
How do they differ?
Yeah.
Sorry, maybe. I don't know.
Maybe some other people want to become a part of this discussion, that we don't reduce this just to 3 people, please. Here, look.
I'll just give my own perspective on this issue from a different point of view. I would say from my own thinking about the subject, I think the introduction of decoherence into this discussion was a step backwards in terms of the physics of measurement and trying to understand why things happen. And you can see that in a variety of ways, but perhaps the most clear one is what Lev already mentioned, which is that in experiments, people try very, very hard to avoid environmental decoherence. To see quantum effects and to be able to do quantum experiments, a great deal of care is taken to reduce interactions with uncontrolled environments. And so really the issue is not that physicists for a long time have understood the role of decoherence. And in some sense it's the physics of dirt. It's the physics of things you can't control. But in principle, if you can control this environment, if the environment is very simple, then that becomes a more interesting question. We're going to be able to quantify that environment, to understand the environment. But what decoherence does not provide is not provide what outcome occurs. It says I get reduction of interference, I destroy my coherence, and I say I have some diagonal density matrix in some basis that's preferred. But that particular eigenvalue, or the particular position or eigenstate, something like that, it does not tell you what that is. To get something like that, you have to add something more to the theory. You have to add many worlds, you have to add classical coin flips, something like this. And so in my point of view, I think decoherence doesn't really tell you anything fundamental about the physics of measurement. It's really something that is, in my view, a distraction to the field.
Yeah. Anyone else?
You're perfectly right that before the measurement, you want to get rid of decoherence in order to get quantum effects. But note that any detector is always constructed such that it produces internal decoherence. Any detector. Otherwise, it won't work.
Somebody else? Here, Nathan, that we don't all the discussion.
Yeah, I wanted to point out that on top of the possibility of decoherence, the measurement also produces a signal, which we actually read off the apparatus. And this signaling process is clearly has a direction of time. It's irreversible. So well, okay, I'll explain why. Usually, people use the grandfather paradox as a reason to say that retrocausality is impossible. And they are right in the sense that you cannot have signaling in both directions in time in a consistent manner. Now, there's a problem here. Let me pause and explain. The problem is that some people are looking at a model or a theory of the whole world. And the theory of the whole world doesn't have inputs and outputs. So it's difficult to describe what signaling means. However, if you want to apply physics, you usually apply it to subsystems. And some subsystems, like optical cables and so on, we perfectly know how to describe them physically. And they have well-defined inputs and outputs. You have, if you want to describe in detail what's happening in the optical cable, you have to specify what the signal is. And you also always specify the signal at an earlier time rather than at a later time. It propagates from the past to the future. We have the same thing in classical physics. The example I used had a string, so you're pulling one end of a string and you're sending a signal to whatever is on the other end. In this type of model, whatever is determining the first part of the string, the position of the first part of the string, it's an external variable. It's input to your physical model, and therefore it's not a description of the whole universe. You're describing just the string, and it has external inputs. And the symmetry of the time reversal symmetry of the equations, there are also always some additional rules which are added. So the initial conditions are treated differently from final conditions. You always break the symmetry in this way so as to produce models that describe signals propagating to the future rather than to the past. And this type of irreversibility is present also in measurement situations because whatever you measured is going to be signaled to some other device which will maybe display it to whoever is watching the experiment.
Somebody else? Okay, so let's ask somebody else. Lev thinks Eddie has a comment because he disagrees with these things. Yes. Yeah, you didn't know you have a comment. Now you know. You just discovered. He has a privileged access to your mind.
This idea if density metrics formalism change the view of the coherence or what?
Oh, that's a good question. I don't think so. I think point of view, it's the same formalism, and maybe it's more natural to think about mixed states in general when we have decoherence. So, yeah, the question I had was the exchange between Lev and then maybe Simon, and then Don's comments earlier. So it's not sure what was the final answer to that. So Don was asking whether decoherence resolved the preferred basis problem, and I think Simon's answer is that it does, to the extent that for quasi-classical domains, it's more or less unique. Is that right way to think about this? Oh, okay. So the answer to Don's question earlier was, although there's infinite many possible bases, consistent, the quasi-classical domain is more or less unique. Okay, right, okay, thanks. Okay.
You have Tim.
So I just wanted to make a historical comment from my own personal history, actually, which goes back pretty far here. Not relevant to anything except the questioning seems to be dying out a little bit, which is that when I got started in all this business, the understanding of what was called many worlds, which I think was really developed out of the original relative state formalism, which does not mention and does not need decoherence in any obvious way, and is also quite different from my understanding of what's now called Everettian quantum mechanics. I don't think you see it in the relative state paper. The normal way people talked about it, whether rightly or wrongly, was they said, okay, this somehow or other, this theory postulates many worlds, and you say, well, what are these worlds? Well, there's a preferred basis which comes from who knows where, right? God. Take the universal quantum state, express it in terms of this preferred basis, and the worlds and their measures are the squared amplitudes. And therefore, to even get into this business, if you understood it that way, you needed a preferred basis. And then there was a whole bunch of time of people, well, where does this preferred basis come from? And then the idea was that decoherence would be a way to pick out, in some sense, a preferred basis by dynamical considerations. I guess it's not obvious that any of that is left in the modern way that decoherence is used. At least it seems to me a very different kind of picture, and one where at a moment people thought decoherence was doing an important job. And I guess maybe the historical, my sense is that the way decoherence is appealed to now just isn't doing that job, right? It's not like it's doing a different job. So I mean, maybe it's just a question whether the people who actually use it now and appeal to it feel like it's doing a different job, or whether my sense of this history is off. I mean, but this is what I got from my own experience of it.
David and Simon answered that question, and then we're going to go to...
Yeah, I mean, that seems broadly correct to me. I mean, one way to catch it out, I think, is that for a while people thought the question was, why was there one base? Why was the preferred basis one basis rather than another basis? And then you particularly see this in sort of 1980s periods, like David Deutsch's version, where it's like, okay, there needs to be a basis, and I'm going to have to stipulate it and actually put it in my formalism, and now which basis is it going to be, and it's going to be picked by a Schmidt decomposition. I think that question sort of morphs into why any basis at all rather than no basis, and I think that partly comes from I mean, at least within philosophy, I think physics was more committed to this all the way through, but within philosophy, it comes from an increasing prevalence of the idea that the virtue of the many worlds theory is going to be that it doesn't need to modify the formalism, in which case the obvious question isn't so much why one basis rather than another, but why is unitary quantum mechanics something describable in multiplicity terms at all? And so then you get the sort of co-opting of decoherence ideas and internal and external into a kind of functionalist logic of that.
Simon also wants to.
Yeah, absolutely. I completely agree with David, but I'd say something a little bit more. I think there is an understanding of what Everett was doing, which is much clearer from his long manuscript that eventually was published as Theory of the Universal Wave Function in the 73 book. One chapter of that is what made it into the 57. And I think that the relative state and the emphasis on the relative state a lot of it was down to Wheeler. And we read Wheeler's supporting note that was published with the 57 paper. It's all about the relative state, ends with his ringing endorsement, there is no escaping the relative state, and so on and so forth. But actually the relative state is really rather a trivial idea. It's just the idea of a correlation. It's just not a big deal. So Everettians can vary enormously on that. So someone like Jeff Barrett places huge weight on the relative state, a sort of relational view of reality and so forth. I, in a lot of my writings in the 90s, placed a huge weight on seeing parallels between relativization of tense that's going on in space-time terms, and saw this relational notion as somehow important. And if you look, for sure, the relative state business feeds into a broadly structuralist picture. And sure, I take a broadly structuralist view of a lot of physics and more. So that's just one comment on the relative state. Another comment is on what has decoherence theory got to do with what Everett did. Well, one way of looking at what Everett did was to take that unitarily evolving quantum state in the context of a measurement process, which is a highly specific, somewhat contrived situation. You've got, a very special Hamiltonian, and you're supposing you've got a macroscopic structure that will behave as a measurement device. But anyway, given those artificialities, nevertheless, the name of the game was to view in the unitarily evolving state a way of breaking it down into parts, each of which tells an intelligible story of macroscopic goings-on. And that business of, I've been starting to call it a vertical reading of the state, and actually it picks up on an example that David gave 10, 15 years ago. So many wonderful ideas go back to David. He took the example of a beam of light in the radiation field. And you can have two beams of light in a radiation field. But then you could think, oh, what if a beam of light has got degrees of freedom of its own? Let's talk about the degrees of freedom of the beam of light, and then that it's in a superposition of pointing in two different directions at once, and that's an incoherent and an impossible thought, and we've somehow gone wrong, and what are we to make of this situation, and so forth. Whereas, of course, the right way to look at the two beams of light is we can look at that radiation field and we can break it down into certain kinds of states in a superposition evolving according to beam of light rules, namely rectilinear propagation, somewhat collimated, and so forth. So that generalizes. We can look at and this would apply to any linear theory. It could be in acoustics, electromagnetism, various other ways. To what extent can we view a complex field, typically a field, electromagnetic, acoustic, whatever, could be liquid. To what extent can we get a simplified description of it in terms of this vertical readings, in terms of processes going on in a superposition? And the answer is they're all over the place in classical physics and linear theories, and the answer is in quantum mechanics they're all over the place too. And decoherence theory in particular, you look at these master equations that people like Zurich got out and Gauss and Zeh got out, you can understand those too exactly as vertical readings of the state, just like Everett. So I do think there's a real continuity in how to interpret quantum theory stemming from Everett, more obvious from his 73 publication, and more obvious still over the last 15 or 20 years, the work that we've been doing. So that's
Okay, there's a time for one more question or comment, and then we're gonna...
It's a different topic though, so maybe...
You want a quick one? Yeah.
Thank you. Well, thanks. I'm definitely no expert on decoherence theory, and my background, my recent background in quantum theory comes from the quantum theory of computation, but I still like to think in quantum theory of computation to understand decoherence and branching and how to make sense of unitary quantum theory. So if we think of a universal quantum computer, it just applies fully unitary quantum theory, and suppose we have one which does Shor algorithm. A question that I still not sure I have an answer if Lev would say yes or no, Simon would say yes or no. Is there any branching while the quantum computer is doing Shor algorithm? It has some probabilistic algorithm. Yeah. Okay, so I'm fine either way. It's just that to me the whole idea is to keep unitary quantum theory, look at the universal wave function, look at patterns into it, and when it does Shor algorithm, what it does is at some point, it branches, and it does a rebranch to spit out the answer. And so I think that we're sort of missing a big part of the whole discussion of quantum theory if we just speak of branching and not rebranching. The quantum interference is precisely some interactions between different terms in the wave function, and that is rebranching. Now, where decoherence comes in is it precisely explains how a poor lost photon running into your quantum computer will ruin your quantum computation because it will get differentiated, and so it will get entangled with your quantum computation, and so it will prevent your quantum computation from being able to rebranch. And this is where splitting sort of occurs, where for all practical purposes, we have to run after that photon, and most likely with all the other photons would have ruined my quantum computation, to do rebranching. And that's, to me, that's the whole idea of decoherence. It's just, the state is still pure, obviously, it's unitary quantum theory, but if you want to make recohering stuff, you have to run after so many witnesses that it's for all practical purposes undoable.
One last, really the last comment from David. You want
just to put that comment in the context of the early decoherence framework. So I think you described the Shor algorithm as the very delicate and precise creation of a classical domain, a quasi-classical domain, and then the very delicate and precise dismantling of that in just the right way to get the interference effects out. It's a good example of where decoherence in a quasi-classical domain is not happening because of the dispersal of stuff across across a large internal or external environment. It's happening because we very deliberately and carefully built it that way and kept it working that way.
Okay, Lev, and then heading.
Just, Charles, there was a kind of big, or maybe still there is a controversy. If does many words help quantum computation and quantum, and there are some people say that it's really, there is experimental, there is fact. Many people in quantum information are many worders. And there are few who kind of viciously says, no, we don't need it. And I think there is some confusion. I think David Deutsch got inspiration, and his quantum computer, we have parallel computation. Each computation is kind of a word. And then using out of these words, we kind of cleverly make superposition and get interesting data. And this is how quantum computer works. But the words of quantum computation are words because it's different kind of computation, so different stories. But these are not branches of Everett, which we have macroscopic objects in different positions. David essentially said the same. And Lev is the same. So the words in my story, macroscopic object should be in different state. If my quantum computer makes different computation, it's still just in a superposition. I will not say that there are many words when I use quantum computer. My quantum computer in quantum superposition. I need macroscopic object in different place. Then there are different words. Different internal quantum state or even macroscopic quantum computer are not different. So at least something we don't know. Let's maybe help for it. No. The whole idea, quantum computer will not work if you will. This is why I'm really pessimistic that it will be really useful quantum computer. It's very useful that all this quantum technology will bring many results, and the quantum computer bring many milliards, I think, into this quantum technology. This is the use of quantum computer as I understand it.
On that note,